Okay, the last topic of this chapter is the analysis of the low and high cutoff frequency. Okay, so basically the analysis for the low cutoff frequency is actually we will do the quite similar approach or procedure. We apply the quite similar approach with the same approach that we use for the BJT circuit. And then please take note that in this course we only cover the cutoff frequency analysis for common source circuit only. So as you may know that for the MOSFET we have three big configuration in terms of the whether this is common source or common drain or common gate. Okay, for the mid-band we cover all those three common circuit, but for the frequency response we only cover the common source circuit only. Okay, so in this slide we do some revision on the difference between the low frequency region, mid-band frequency region, and mid-band region and high frequency region. So this is in terms of the equivalent circuit, and we want to relate it with this frequency response, or we call it a Bode plot. So the Bode plot here, this is the Bode plot of a typical amplifier. So at the middle is the frequency range, where we call it a mid-band, where the gain is stable at the highest point. So we call it A mid. So this is a mid-band gain. So this usually for the range of the mid-band, we call it a bandwidth. This is the range of the frequency where the amplifier operate in optimum condition. Okay, so as the frequency decrease towards the lower frequency, the gain will decrease, and then at the certain point where the power gain become half of the mid gain. So this is the point where we take as a cutoff frequency. So this is your cutoff frequency. Okay, remember this is a power gain. Usually for our course, we do not use the power gain as much as not so much. So we use the voltage gain. So this is a voltage gain. So the cutoff frequency point is where the gain is decreased, which is AV mid minus 3 dB. So the decrease of 3 decibel is equivalent to the changes of the power gain into half. Okay. So and then when the frequency increase towards the more high frequency operation, so we will also observe the similar trend where the gain decrease. So using the condition AV mid minus 3 dB, so we can identify the high cutoff frequency. So this is the high cutoff frequency. Okay, this is the explanation on the Bode plot. So what's the difference between the low frequency, mid-band, and high frequency region in terms of the circuit analysis? So when we do the analysis on the gain, we will do the analysis based on the equivalent circuit. Okay, so how we draw the equivalent circuit, and specifically the component inside the equivalent circuit will affect our analysis result. Okay, for the mid-band, for the mid-band region, so usually what we do is we will consider the coupling or bypass capacitor to be short, because we assume at the mid-band region the impedance of the bypass and coupling capacitors is small and can be ignored. So it's small and can be ignored, and it is small at the point is equivalent or comparable to the impedance of the wiring or the connection. Okay, so this is the coupling. So in the mid-band equivalent circuit, you will not see any coupling or bypass capacitor in the equivalent circuit. Okay, so and then inside the device or transistor itself, we have what we call it a parasitic capacitance. So this parasitic capacitance is very small in picofarad order. So in the mid-band operating region, so this parasitic capacitance will have the quite high impedance. So this is quite high at this this is comparable, not comparable, this is significantly higher than the value of resistance inside the capacitor. So for this case, the parasitic capacitor will not appear because it is considered as open circuit. So we will not draw the parasitic capacitor in the mid band region. Okay, so when the frequency decrease, so what happened to the impedance of the capacitor or capacitance? The frequency will increase. Sorry, the impedance of as the frequency decrease, the impedance of the capacitance will decrease. So because the ZC is proportionally inversely proportional to the frequency. Okay, so what happened to the coupling and bypass capacitor at this frequency region? So the impedance will not be comparable, it will not be small, so it will have a value of impedance that cannot be ignored anymore. So you need to consider this impedance. It need to be taken into account to analyze the performance of the amplifier. So that's why the coupling and bypass capacitor will affect the gain of the amplifier. Okay, so but for the parasitic capacitance, although the because the frequency, when frequency decrease, the impedance increase, so the resistance will be further increased. So there will be no change in how we consider in terms of the consideration of the parasitic capacitance. Parasitic capacitance will be still assumed as the open circuit because the resistance is still high. Okay, that's why for the low frequency region, we will see the coupling and bypass capacitor. Okay, so next we go to the high frequency region. So high frequency region, when frequency increase, the overall impedance decrease. So the coupling bypass capacitor will have a very small value. So in this region, it can be replaced by the short circuit. Okay, for the parasitic capacitance, at the mid band and low frequency, the impedance is very high, but since the frequency increase, this impedance will decrease. It will decrease from the high value into the moderate value. So this moderate value need to be taken into account when we do the analysis. So in high frequency region, this parasitic capacitor need to be considered. So this capacitance will appear in the equivalent circuit. Okay, so I have mentioned about the parasitic capacitance. So what is parasitic capacitance? Parasitic capacitance is the capacitance. It's not a component that we put in the circuit, but it is the capacitance value that available or exists in the MOSFET structure. So this is due to the structure of the device, or sometimes this is due to the bias condition. So sometimes the capacitance inside the MOSFET will change depend on the bias condition. For example, when the drain voltage is low and high, the capacitance value will change. Will have a different value depend on the voltage applied to the device. So this is the capacitance. So if you see this device structure, this is a device structure. This is the device structure of the N-channel E MOSFET. So we have here, this is the source, and this is the drain, and then this is gate. So the black color here is a metal electrode, and then the gray one here, this is insulator. So this is insulator. Okay, so the basic structure of the capacitor is a metal plate, two metal plate or two conductor. We have two conductor, and then we have at the middle of the conductor we have insulator. Okay, so from this structure you can identify several points where we can have the capacitance. For example, between the gate and the source we have this capacitance. So this is between gate and source, we have this capacitor because this metal, insulator, metal. Or for example here, this is metal. Between gate and drain, we also have this capacitor. So this is CGD and this is CGS. Okay, and then between the gate and the channel here, we also have the capacitor. Okay, so in fact, actually, if for the more specialized or more detailed analysis of the MOSFET, you can identify many contribution of capacitance. For example, inside here there will be also a capacitance, and then there will also be capacitance here. Okay, but anyway, for this course, we will simplify, and then we will only consider a certain parasitic capacitance inside the transistor. Okay. Okay, for example, let's say if this is the symbol of the MOSFET. Okay, this is symbol of the MOSFET. You have, this is the drain, and this is the source, and then this is gate. Okay, so the basic rule, you can simply say that between the two terminals there will be a parasitic capacitance. Okay, for example, between the gate and drain we'll have the parasitic capacitance. This is CGD, and between the gate and source we'll have another capacitance. It's called a CGS. Okay, so and then if you consider some like this, you can also say that between source and drain there will be a parasitic capacitance, CDS. Okay, but however this CDS is not that significant because in terms of the device operation, between source and drain there will be no metal insulator metal structure. So the CDS, in most time we ignore this. Okay, so but anyway, for this course, so for example, in the assessment for the test, quiz, or final exam, you make sure you identify the given parasitic capacitance. If the parasitic capacitance, like say CDS, is not given, you can ignore the value. So if the CDS is given, so you need to take into account the value. Okay, so this is the parasitic capacitance. Okay, beside of this parasitic capacitance inside the device, we also have the capacitance due to the wiring at the input and output of the circuit. So this is the CWI, this is wiring input, and we also have CWO at the wiring output. Okay, so anyway, this one is the wiring input and wiring output is the same what we have considered during the BJT amplifier circuit. Okay, so I have mentioned that for the frequency response analysis, we will only consider the common source. So let's consider this circuit. This is a common source amplifier with a bypass capacitor. So where is the bypass? This is the bypass capacitor. The full equivalent circuit will have capacitor and parasitic capacitance. So how the equivalent circuit will looks like if we draw all the capacitor and all the parasitic capacitance. Okay, so let's draw that. So we have the V signal. This is your V signal, and then we have here, this is your R signal connected to the C1. Okay, and then at the input we will have the parasitic capacitance of CWI. Okay, so and then we have the R1 and R2. Okay, let me for this case I combine the R1 parallel with R2. Okay, and then we have here, this is the gate. Okay, this is the gate. This is your VGS, and this is the source. Okay, at the source we have the RS, and we also have the bypass capacitor CS. Okay, between of the gate and the source we have the CGS, the parasitic capacitance between the gate and the source. So this is CGS. Okay, between the source and drain we have the current source GM-VGS. Okay, so if we consider we have this capacitance between the source and drain and source, we can put the CDS here. Let's say I put here, this is the CDS. Okay, and then between the gate and drain there is also a capacitance CGD. So this is your CGD. Okay, and then we have here, this is the RD. This is your CWO, and you have the output coupling here, and you have your RL. This is C2. This is the equivalent circuit with all the capacitance and all the capacitor. Okay, so in the low frequency region, the parasitic capacitance will the parasitic capacitance will be removed. We remove the parasitic capacitance. What remain is only the capacitor. So the capacitance is removed because it's considered as open circuit, high impedance. So the low frequency region, the equivalent circuit will looks like this. We have the V signal. This is your R1 parallel with R2. RS, CS, this is your GM-VGS. This is your C1, R signal. This is RD, RL, this is C2. This is the equivalent circuit at low frequency region. So all the capacitor appear because at this point you cannot ignore the impedance of the capacitor. Okay, at the mid band, the capacitor we replace by the short circuit. Okay, so can write down here. So we'll take some time. This is just to show you how what is the difference between the mid band and low frequency as well as the high frequency region. Okay, at the source point here is directly connected to the ground because we have the bypass here. The CS bypass to the ground. This is the RD, and then this is your RL. Okay, this is the mid band. Okay, when we move to the high frequency, what happened? So we from the mid band, we need to add the all the parasitic capacitance. So at the high frequency, okay, we consider the mid band. This is your V signal, R signal. This is R1 parallel with R2. Oops. See my mistake. This is your VGS. This is RD. This is your RL. Okay, this is the mid band. At high frequency, you need to add the parasitic capacitance. So you have the parasitic capacitance as the CWI here. At the input, this is your CWI. And then between gate and source, we have CGS. Okay. And then between the gate and the drain, so we have here, this is your CGD. Okay. And then between drain and source, okay, I put this is dash line because in most time we ignore the CDS. Okay, and then at the output terminal we have the CWO. So this is the high frequency equivalent circuit. Okay, I'd like to emphasize on the CDS. If the CDS is not given, so you can ignore the CDS. If the CDS is given, you need to draw the CDS. You need to include the CS in your equivalent circuit.